not visible. Is it supposed to be visible?
Yeah.
So the spectrum we all learned in physics, right? What are the visible range? What's the visible range in the spectrum? Probably undergraduates don't learn this. It's just when you have to deal with optics. What's the visible range in general, roughly?
It's under ultraviolet and infrared.
I know, but
And
wavelengths
infrared
wise.
radio.
I don't know the numbers.
So what's so if this is wavelength, right? What is this color here over here? For larger wavelengths, and after that it's invisible. What is this color?
Purple?
Red, right? Here is like blue or purple, okay? We don't say purple, do we?
Indigo?
Turquoise?
00255.
That's zero. That's off.
Oh.
That's nothing. That's dark.
255, 2550.
Okay, so that's wavelengths, and usually here is roughly 750 nanometer. Here is usually like 420 nanometer. So in that range is called invisible. So this is visible, and these are not. And over here is called infrared. Infrared. Did I spell this right? Infrared or IR, right? IR. And this is UV, ultraviolet UV. So you are not supposed to see it, right? Like when you are using a remote control for the TV, you are not seeing a beam. That'll be scary. You see a beam. It's not visible, so you are not seeing a beam to control the TV or projector, right? Because it's IR, it's not visible. However, I made a way to see it. Look at it. I just recorded before the class.
Oh, yeah, 'cause your phone camera can pick it up.
Yeah, your phone camera. So the photo sensor, the CMOS imagers on your phone can see it. Okay. So if you see here, basically that little dot is the IR signal from the LED. IR LED is a light emitting diode, and you can see it from here on the board, right? On the board schema layout. So it's connected to this BJT as a switch on the top of the board. It's hard to tell, so if you have the board, you can grab and take a look at it. It's a little tiny LED on the top, and the receiver is on the left-hand side of the board. It's called a decoder or receiver. It receives the pulses and decode it and convert it to just pure digital signals. And it's emitting. It's the LEDs over here, receivers here. How to expect it's gonna receive it? How do you expect to use a remote? It's able to receive it, right? I bounce back and forth, so I can use a remote and push just towards the wall and still able to receive it, right? So the IR can bounce back and forth. So you are looking at this IR LED on the board. Definitely, this receiver will receive it from somewhere else. Yeah, it's very sensitive, and also this one is receiving a very high current. I think the in-lab asked you to test it, and I think somewhere around 300 milliamps. So it's considered as pretty high current for the LED, so which means it's super bright. You couldn't see, but it's very bright. All right, so don't directly look at it. Did you see anything? It's hurting your eyes, so don't directly look at it. You can find out it's working by using a camera, but you have to turn off the ambient light in order to see that from the camera. So sometimes we don't really have to do it because you can always probe your microcontroller to see if you are sending out that pulse to drive that LED. You can probe it electrically. However, if you want to verify that, so for example, directly feed that electrical pulse, right, digital pulses or signal to the LED. It should turn it on, right? Should turn it on. However, the receiver is not receiving anything. So in that case, you can use a camera, turn the light, and look at it, see if the LED is really blinking under the camera to check if the LED is dead or not. But what you can also do is just to swap the board, right? Just replace with a different board, see if that works. Just tell you the different ways to verify the functionality of the board. And you can see here, there's a jumping wire, okay? The jumping wire. And let's go back to the schematic. Lab 6. Oh no, sorry, the schematic, not lab 6, schematic here. All right. So it is over, where is it? Oh, here. Okay, it's over here. So you need to understand what's going on. What's going on here? RC1 is a pin. So we use the pin to control the LED. Makes sense. So RC1 comes in, but there isn't a connection if you don't put a jumping wire or jumper over here. So you put a jumping cable or a jumper over it, making the connection. So which means the electrical signal being sent by the microcontroller through PWM, so the pulses will be sent through this jumper to the BJT, which is the switch, turned on and off, and here's the IR emitter. Okay? So you are controlling the base. Why do we use the BJT though?
What is a BJT?
Oh, BJT is a bipolar junction transistor, and you have learned that in electronics or no?
We
Not
just
yet.
got to it in devices like today.
Oh, okay. So it's amplifying the base current. It's not that important though for here, since we're not analyzing the details. So it's just a switch. Here you turn on and off. You are able to turn on and off this branch. So here's VCC, it's a power supply. If you turn this on, the channel here is on, so it's going to flow current through it.
So it's like
It's a gate, yeah, it's a switch. And it is able to amplify the base current through this collector current by a certain level. It's called beta, usually it's 100 or something. So times the current, but that's not important though for here. We just need to know that you send the pulses, switches, you give a on, you give a 1 here, and it's going to turn it on. You give a 0, it turn it off. So 1 will turn on the LED. 0 will turn off the LED. Make sense? So when,
How come? Because like our other LEDs, we had like VCC, and then you want to give it like 1
Yeah,
to
yeah.
turn it off.
Yeah. So
So
you
the
turn on,
voltage
it's a
drop.
channel here. It's like a channel, like a switch. So the transistor is a switch. You give a 1, you turn on this little switch, so it flows current from VCC to ground.
Oh,
Okay, from top to bottom.
Gotcha.
Yeah, since you already grounded and powered it up here, put it up here already. So it's waiting for this switch. If you turn on the switch, it flows the current. Okay? So you can imagine that if I send a pulse, it's able to turn it on and off or toggle it. Okay? And that IR signal will be sent through here. Okay? Even though it's not directly facing this receiver, but it will receive it. Keep that in mind. Okay? Understand that? So whenever the signal comes out from, it's magical, right? So why it's able to receive and decode it precisely. So it's gonna receive it. Then the decoder is over here. It's an IC chip. It's not just simply a transistor. It receives the pulses and convert it to pure digital signal instead of PWM. I'm gonna show you what the waveforms look like, but now I just need to know that this little receiver here is on the top. It's a receiver. It's also a transistor. Photosensitive transistor is going to receive it and send and decode it and send the out as a pure digital signal through this line to RC0. So RC0 will be what? Input. Will be input to the microcontroller. RC0, keep that in mind, all right? So this is output of the microcontroller because microcontroller output the signal to drive it, and then signal received being decoded, and then we'll send the signal, put the signal to RC0, and will be read by the PIC through RC0 pin. Make sense? That's everything about the hot wire. So if I just want to probe the PWM, looking at this layout, see here is disconnected, right? You need a jumper on the top, okay? But now we don't have a jumper, for example. I don't put a jumper here. So in the in-lab, I program my PWM. I'm trying to create a series of pulses. I download it to the microcontroller. I just want to probe it. Do I need to connect it to the IR? Do I need to connect to the IR? I just need to look at the electrical signal, not the IR yet. No, where do we want to probe? Just look at the PWM.
C1.
Here. C1, here. It's connected, just probe it. Without a jumper. If you connect a jumper to it, what's going to happen?
You turn on the IR.
You turn the IR, why is bad?
Could hurt your eyes.
Yeah, if you just sometimes you forgot that, you didn't pay attention to it. You're looking at the wires and trying to figure that out, and then looking at it, staring at it. That could be bad, right? So you don't have to always keep the jumper on the top, unless you really need to test the IR signal and receiver, that kind of path, which is actually in at the end of in lab 6 or the lab, actually. So keep that in mind. Now let's talk about PWM. Okay, this is PWM, and I verified it. The duty cycle is not that important. What's that?
So can we just make this like an off button for a TV? Like get the right PWM for IR and just like turn people.
Yeah, if you code it correctly, yes, it's gonna be the same PWM. It's always 38 kilohertz, and the pulses doesn't have a reference, just the light pulse, right? It doesn't like the optical signal and the electrical signal. You have 5-volt system or serpent servo systems, and they need to be grounded in order to communicate between each other. But optical, you throw the photons into the air. There's no reference. It's just light pulses, okay, in the air. And whenever there's a receiver receive it, you don't need the reference, just the light pulses. Then it will be decoded, so it's compatible in between all the different systems. You don't need the reference. So 38 kilohertz, keep that in mind. That's an important parameter over here. What's really happening is you send that electrical signal. Now you just have to keep that system hardware in your mind right now, because sometimes you'll see a signal, you don't know if it's output, if it's optical or electrical or receiver, transmitter. Now, since I already went through the hardware stuff, you know what's happening, okay? You have to send electrical pulses from your microcontroller, their electrical voltages, to the LED controlled by the transistor, and that's going to convert that pulse into optical pulses. All right, it's going to be photons, and the photons being sent through the air and being received by the decoder, and the decoder is going to output this 101. Now everything after this, everything is on the board electrically, nothing in the air anymore. Make sense? So what about this? What is this pulse? See if you are getting that.
Isn't that the?
Is it electrical pulse or optical pulse?
That'd be
From where? Where is this pulse from?
that's the electrical pulse from the sender.
Yeah, from RC1. Okay? So this is driving what? Driving the base terminal here. You put a jumper here, it's going to drive it. Okay? And then you got an optical signal. Okay? The optical pulses. Okay? There's no way, at least that we don't have a way to display the optical pulses, so you need to know this is electrical pulses. Electrical pulses being sent through the optical pulses in the air, and that is being received by the decoder. Decoder decode it, and it's going to output a digital pulse here. Make sense? That's the whole process. All right? Make sense? Okay, cool. So how the decoder decode it? It's pretty easy to do. I'm not seeing the hardware, but we don't have to worry about that. So what's happening is, if this kind of optical pulse is being received, it's gonna output a 1 whenever you have pulses. Actually, it's the other way. You know, that conceptual image is wrong. it's the other way. Let me show you. Pulses is giving a 0, depending on the decoder type, okay? So this decoder on the board is gonna give you a 0 if you see pulse series of pulses. See? Pulse is giving you zeros, and zeros giving you 1. Doesn't matter. You can modify the decoder whatever you want. Okay. But anyway, so the phase, yeah, it takes time, right? It takes time. So this is again, what is this signal from where? Electrical from where? RC1. Okay. RC1 send the first pulse, and keep sending the pulses, and these are PWM pulses. We already learned how to do it. So this lab is going to use PWM pulses to code it into a signal. Okay, so PWM pulses comes, being sent to the BJT transistor. BJT transistor converted to light pulses. Light pulses sent to the air. The light pulses, photons in the air being received by the decoder. Decoder receive it, decode it, boom, put it here. So here's the time delay. The time delay shows all the whatever the description I just made. Okay. BJT, photons, air, receive it, decode it, boom, comes back to the board, receive it.
How come the decoder goes low once it receives the signal?
I said you can modify the circuit by whatever you want. It's just a pull down, pull up thing,
Gotcha.
right?
So that just matters how the resistors are either connected to ground or to
Yeah,
VCC.
yeah. You can modify the circuit easily. But anyway, it's whenever you see pulses, it's going to give you a 0. Whenever you send a 0, it's throwing a 1 from the output. We just need to know how that works. And then, so this data comes in, right? Comes in. And this data is being sent to the UART port. Now let me ask you this question, okay? Let's make sure you guys understand it. So this signal arrives where? This signal arrives where? RC0. RC0 is where? It connects to where? To RC0 of the chip, right?
Microcontroller?
Yeah, my controller. Is it reading or output or reading? So whatever you hear will be read into here. Okay. Then what?
In the microcontroller, wouldn't we want to route it to UART?
Yeah, to UART and then to where? If you want to see what's going on. Serial UART to your POTI terminal and display whatever has been sent, which is very magical, right? It's amazing. So you hear in your serial, you type hello world, okay, and that will be encoded into digital signal and being sent to where? You press a key, you want to send it to where? RC1. So that hello world, whatever text you want to send, will be encoded and as pulses and being placed at RC1. And that pulse will be converted to optical signal, will be pulses, okay? And then we be sent to the air, okay? And the decoder will sense it through the photo transistor and decode it to digital signal and place it to here back to the microcontroller, right? So the microcontroller has RC1 here, RC0 here, right? RC1, I send the PWM pulses to that IR LED, send it to the decoder, decoder comes back, and digital signal being received by RC1, RC0. And then I keep it inside. And then I manipulate it, convert it to UART signal, and send it through the USB back to the laptop, to the monitor so you can see it.
We're gonna be in
Why do we have to do it?
We're gonna be in B-dubs and click the button and turn the TV. You need 32 bits though. Can you do that many?
I don't know how many bits are in there for the UART over there, but
Like 8 bits.
Yeah.
it usually just the bytes. So like the buttons on the remote over there, you can actually see it. If you don't use the IR LED on your board, just use that one and try it and see what kind of code you are receiving, and you can look at the code and then encode it, right? Encode it, and then send it through that one. It's gonna do the same thing. It's gonna control that one easily using your pick. Yeah. It's gonna work.
We're gonna be funny.
So
Bring your laptop.
This-
Turn the computer on.
So it's basically you put something, you type something in your UART and send it, and it's gonna receive it through the UART, and you can visualize whatever you have typed and send. Doesn't sound that really fun, right? But this, once it's working, you know exactly what's going on. It's really fun, but the result is not. It's a good learning process. Okay, so now let's get into the PWM. Makes a lot of sense right now. Let me show you. It's relevant to the midterm. Let me get into that first. So helps midterm as well. Okay, let me give a quick quiz question here. If it's a quiz question. Dewey value 120. It's a number counts. Okay. Number of counts. And we are using that 1 to what? 1 to 16 for timer 2. Let's just calculate how long it takes, what's the time, based on this timer and this count. How do we calculate it? This is one of the problems, 10 points on the midterm. 10 points.
For this
Timer
to be,
2 8-bit.
You ask first, Brandon. Yeah.
For this to be assumed, it's FOSC divided by 4.
280. Did you say 280? What did you say?
I said for this to be assumed, it's FOSC divided by 4.
No, for timer 2, counting for duty value, refer to Monday's lecture. We use FOSC, not FOSC divided by 4. We explain that on Monday. Keep that in mind if you're still not clear on that. So timer 2, I'll address your question after that, okay? So timer 2, you have PR2, and you have another one. Oh, that's important. I don't want to see you guys losing points on this. Remember what we did on Monday?
It's actually 10-bit.
So it's a 10-bit timer 2.
Well, it's just because the 2 bits
Yes.
only have the FOSC, not the FOC.
Exactly, yeah. So this LSB is being toggled at this, and this is being toggled as this. Seal this in your mind. If you don't understand after the lecture, ask me, okay? 20 points, probably 2 or more problems on this. We can figure that out. Don't worry about that, okay? I'll be in my office this afternoon, so after the lecture, visit, so we can figure that out. Okay? I'm not going home today, so since I have another student visiting at 3 p.m. Your question, Kobe?
Is timer 2 8 bits? Timer 2 was 8 bits.
Timer 2 is 10
You
bits.
showed it.
Timer 2 is 10 bits. Timer 2 is always 10 bits. It's always 10 bits. It's 8 bits sometimes. That's why it's confusing, right? That's why we spend the whole Monday to figure that out. We only use the 8 bits of timer 2 to match PR2. But basically timer 2 is 10 bits.
So we use PR2 when we're using timer 2 like a normal timer where we're writing to it just regular values, but we use those other 2 when we're doing PWM.
Our other 2 what?
The other 2 registers that you talked about last class that are also 10 bits,
Yes.
the high and low. Do we only use those when we're doing PWM?
You can use timer 2 for other purposes, but we are not. Definitely you can use timer 2 to count for other purposes, right? But it's always, so timer 2, the way that works is always matching with this one to turn on the flag. That's how that works.
Even during PWM?
Even doing something else. PWM, of course, that's what we do, right? PWM, that's what we do here. So timer 2 matches this one, but it matches from this bit, this bit, start from this bit, not this bit. It's this LSB, not this LSB.
So then we're
Keep
using,
that in mind.
So then we're using FOSC over 4 then, because we're
FLC over 4 for this guy, not for the one on the top. That's why we spend the whole Monday to address that problem. I know it's hard to understand. That's why I myself always also spend a lot of time on it to figure that out, because we see inconsistent results from Dr. Carlson's website and other places, right? That's why we got confused. Now we already clarified on that. I'm going to show another evidence, and this is the way you want to go. This is correct. What's that?
What's the topmost one?
This is CCPR1L, and this is DC1B. That's the 10 bits for the duty value. That's the duty value, 10 bits. Should we delay our midterm to next Monday? What's that?
So it's just 120 divided by 64 divided by 16, right?
Yes.
Yeah, a million.
Delay to Monday? Don't want to fail all you guys. What's that?
And so when you were asking for the time, was that the time when it's high or the time it's low? Like, was that the
Duty cycle is high. Duty value is high.
I just wasn't sure what you were asking for.
Duty value, when I'm talking about duty, here's the duty, right? The percentage will be the duty cycle. Let's figure this out first before we go to the what's that?
So we have our duty value stored in CCP R1 low. What is stored in high?
Oh, okay.
Because I know you said that you like write one into the other one, and I wasn't sure what the point of having the two registers was. So
Yeah,
should
that's
we just
also,
break down that a bit.
yeah. This is CCPR1 high, right? 8-bit. 8-bit. Here another DC is keeping that 2 bits, it's not changing it. So the way that works is, let me just go through that step by step, okay? Okay? So at the very beginning, when things got started, what's in timer 2? 10 bits. 0 starts counting, right? 0, 1, 2, 3, 4. Make sense? So this is being toggled at what?
FOC over 4.
Yeah. What about this?
FOC.
Yeah, 64 megahertz. 16 megahertz. What's that? Okay, let's keep going, okay?
Sorry, I was confused on. I was asking earlier if for the 1 to 16 prescaler, you assumed it's already been scaled by FOSC over 4, but right there you said no, but right there you're showing in the timer 2 it does scale it back to FOSC.
It's not scaled. It is scaled. This is just remember, if I say FOSC, it's gonna be always 64.
Yeah.
Yeah, it's always 64.
But what's going into timer 2 ends up being FOSC over 4.
Yeah.
So it is scaled to FOSC over 4 before
Yes.
the prescaler.
Yeah, like what I said, remember?
So
0, 1, 2, 3, 4. You got that?
Yeah.
It's slowed down by 4 times. Okay, cool. What's that?
That's what I was meaning by is it using FOSC over 4, so it does use.
FOSC over 4 is used for this bit, not this bit.
Yeah.
So this bit is being toggled as this frequency to compare with this guy.
So
Because this guy is shifted. It's shifted by 2 bits. So this is a line is comparing with this 8 bits. However, the duty value is 10 bits. It's comparing with these from here.
Perfect.
Yeah.
So when we're going to do the calculation for duty value, we
Yes.
both scale FOSC by the 1 to 16 prescaler and the FOSC divided by 4.
No. That's why that's the whole point here. Because this bit is being toggled as this frequency. Nobody care about this one if you compare to this one. Just ignore that. This is aligned with this LSB. And that LSB is toggled at 64 megahertz. 10 bits. Same thing as how you combine here, how you compare with this one. Same thing. 10 bits. Toggle this guy at 64 megahertz. Compare with the 10 bits over here.
Okay.
Yeah? So, if you have 10 bits in here, you toggle this guy. Every time you toggle, you get 1 count, right?
Yeah.
If you have 100 counts, you need 100 counts. 100 toggles.
So we're using all of the comparison, and that line you drew at the end of timer 2 in black, that's more of an arbitrary line. If you could draw it just as well 1 to the left, and it'd be FOSC over 8. You just chose to do it there.
No, that's better.
That's a hardware. That's designed by the Verilog writer who wrote the Verilog. It's a line here.
Okay.
So the difference here is, like, the duty value, we use all 10 bits, but for the period register, we're only using those, the 8 bits.
Why do you worry about the number of bits right now? It just counts. You need you know the frequency, so you can get a time. Whatever counts in here divided by this frequency, you get a time.
Okay.
You don't worry about the number of bits anymore. It can be 8 bits, definitely. When it overflows, you have to know it overflows after a certain number of counts. Make sense? What about here? What do I give? What did I give? What's provided? What's provided? What is provided here? Duty value 120. What is this?
Number of counts
Number counts where?
FOS.
and the time. Yep.
LSB stored where? Here?
No.
Here?
Yes.
Good.
Yeah.
Way better right now. Oh my goodness. Okay, cool. 120 stored here, right?
Yeah.
Which one is the LSB being toggled to compare with this whole thing?
FOC over 16.
FOC.
FOC.
FOSC, right?
With the spread.
So counts is given, frequency is given, calculate the time. Easy.
Okay, so the duty value is just based on the 64 megahertz.
Yes.
Okay, got it. Okay.
Before you got that pre-scaled. So now don't get confused. Pre-scaler is something is extra.
Yeah.
This is just whatever already hard-coded. It's a hardware, right? Pre-scaler, you can add to it. For example, I'm talking about, hey, 16, 1 to 16, pre-scaler, which means this one becomes what?
64
4.
over 16. Yeah.
What this one becomes? 1. So,
I have a question. On the exam, will we need to know all of the names and labels for all of the parts of the timer, or just understand it conceptually? Like, will you have a question that's like, what's stored in DC1B? Or will you
and there are all not there are other names. I would just say CCPR1, DC1B. You just need to know that this is gonna be the duty value.
So
That's
you you would have a diagram laid out, and you wouldn't just ask based off of it.
I don't have the diagram like this. I don't have this drawn on the exam. But I'm gonna ask you, if I put this value in here, how long it's gonna take to
So we do need to know
What's the duty-
all of the names and what their corresponding part of
1, 2, 3, 4 names.
Well, yeah, but overall, for all of the timers, all of the parts, we need to know all of the names of them.
I don't have others.
That's the only one?
Just timer 2.
CC. Well, let's just take all of them and put it on here and see if you know all of what they are. Okay. Let's do what is CCP1? What is this?
It's a pin.
That's the pin. Pin for what? For PWM1 module, right? That's a pin. What is this?
Register.
That's a register for the duty value for the upper 8 bits. What is this? YX. So you have 1, 2, 3, right?
The lower 2 bits.
Lower 2 bits. Anything else? It could be 1, 2, whatever, right? You know it's a timer. It's not something else. What is this?
Period register.
Is that period register? Right? PR2, PR1, PR something, PRX. That's a period register. That's it. Give me a second, probably.
Yeah, you're good.
Before I jump too frequently on anything. That's it. What's that?
Okay. So can you clarify, because the low stores the duty value, so what is CCPR1 high store?
Yeah, let's come back to this one. So start counting from 0, okay? 1, 2, 3, 4, blah, blah, okay? Start counting. Okay? It's gonna match which one first?
The CCP1
It's just whatever 10 bits, right? The 10 bits. It's gonna match this one first.
Yep.
Okay? Why not this one first?
Because the period will be larger than the duty value.
Can you make this one larger than this?
The period's not changing, the timer is, right? So
Yeah. These are all constants, right?
Yeah.
Right. Yeah, but
Can you make this one larger than this?
no, you can't because period can't be larger than duty.
But I mean, but why?
Well, because like your period is your high and your low.
I know
Your
that's
duty is
a fact, right? But how you cannot do it? Why this
Oh.
won't surpass this, right? Why this won't go beyond this? Like 10 bits, this is 8 bits. Why this is not going beyond this guy?
Because when you put in the duty value as an 8-bit value, but it's shifted.
Yeah, that's how that works.
To fill in those lower 2 bits.
Yeah. Okay. What's that?
Can we solve this one? So can you show us the calculation?
Oh yeah, cool. 120 divided by what?
64 over 16.
Divided by what?
16.
Done.
Man. That's what it is.
All right, cool.
30 micro.
Oh yeah, 30 microseconds. So you'll know this is 30 microseconds, right? So we are, if I ask you that PR2 I have let's do 100. What's the period? Is that a reasonable question? Give you a count in PR2, ask for period. Is that a reasonable question at all?
Yeah.
Yeah? How to do it?
It's going to be FOC divided by 4 divided by 16.
Yep.
Done, right?
Done.
What is it? So that's
100
oh,
micro.
100 micro, yeah. Why? 64 divided by 4 is 16. 16 divided by 1, right? Just 1. 100 microseconds. Now let's see which one's longer. 100 microseconds longer or 30 microseconds longer? 100 microseconds longer. That's what we want. So the period is longer than the duty, right? And you're still worrying, hey, I just don't want to make that duty value larger than this. Let's pick out values and see if it will ever go beyond it, all right? Oh, it will actually. If this 10 bits is going over like, oh, let's see. Probably not. No, it won't because extended is the same thing. Yes, the maximum number will be equal. That's the maximum. So let's see. What's the 8-bit? What's the maximum? O1s, right? O1s will be what? Divided by what?
FOC over 4 divided by 16.
Okay, that's for period, right?
Yup.
Oh, it's not working anymore. What about this one? 10 bits. 10 bits maximum will be what? 1023, right?
Yeah.
Over
FOC
FOC over 16.
And then wouldn't that just be the same?
Flip this one to the top. Oh, actually you need to plus 1, remember?
Oh, right.
The PR2 function?
PR2 is the
Oh.
plus 1.
Yeah?
But the
Let me, don't want to
but the
confuse
register for the duty value isn't plus 1, right?
No,
It's
why?
just the period?
Yeah, just the
Yeah,
period. People are getting confused even further. Let's go back to the equation. This answers 2 questions, okay?
So when we got 100 micro earlier, should it be 101 micro? 'Cause we're
No,
getting
no. You plus 1, you make 100. See? PRX plus 1. Just keep that in mind. To calculating period, if PR is given, you need to plus 1 to calculate the period. Just remember that. It's given on the data sheet.
So if we're given 100 counts in PR1 or PR1, we would add 1
Yeah.
and then do our
Yes.
divisions.
Yeah.
Okay, gotcha.
So some of these are wrong actually. So we should
So
come back here, right? Plus 1, right? Okay? So this is 101 microseconds.
Okay, so what does CC R1 high store.
Okay,
So
now
all
let's.
the stores are duty value. What's
Yeah,
high
it's
store?
being asked for 3 times by you
Yeah.
this today, so let's
I
do
know,
it.
so I'm not sure I can do that, 'cause I don't
Yes,
know.
yes, I will do it.
Yeah.
Yes. Does this make sense? Are we getting the right value here? It's missing one count, but the maximum, which makes sense, right? So it's not.
Well, we got the LED to be totally off with the 100% duty cycle if we put 0x100.
Yeah. All makes sense, right? So what's the period right now? You flip this to the top. What's going on? 1024 divided by what? Doesn't work. This micro, I hate it. So 1024, right? Flip 4 on the top. So it's like FOSC over 16, right?
Yeah.
And now we use, for the period, we put all ones in it. We got 1023 divided by this. It's not all fully off, right?
Yeah.
So we need to add a 1 to it. So you want to have a, for here, you need a 1 here
So
and
you're
all
also
zeros.
So you're also adding a 1 for the duty value calculations?
If you want to turn it off.
Yeah, if you want to turn it off. Yeah.
Yeah, if you want 100% duty cycle.
Oh, if you want 100%.
Yeah, that's depending on applications, right?
Because it's also
For
10%.
calculations, you don't add to it. Keeping that in mind.
Gotcha. Calculations don't do it, but if
No.
you want to turn it off.
Yes.
Yeah. Makes sense.
Okay?
Yeah.
All clear?
Yes.
Have 7 more minutes. I will be in my office. If you have questions, visit. Okay, make sure you visit. And
Solid.
okay, let's verify it.
It's very.
You're saying, hey, it's on the course's website. It doesn't say so, and also in the in-lab doesn't say so as well. Let's go back and see if I'm right. Okay, come back here in the in-lab. Okay, in the in-lab, I'll let you guys do a calculation. Assume that what's that?
So if you ask us for the period, like on the exam, ask us for the period based on PR2, do we add 1?
Yes.
Okay.
So this is the in-lab code, even though we haven't gone through that yet, but I'm just telling you that the 25 is being used as the duty value for that PWM pulse to drive the error LED, okay? No problem on that, right? Okay, no questions on that. So use 25 to calculate the duty, the time. 25 is the counts. 25 is the counts, being loaded to where? Oh, still haven't answered your question. So now let's do it. So 25 is being loaded here, right? Okay. And whenever PR2 it matches here, this will be latched into CCPR1 high. Okay, and this combined with these 2 bits will be used to compare with this guy.
Gotcha.
Why it designed that way, and that's probably one more cycle. Taking one more cycle here, that's probably why you have to add 1 to PRX. I don't know yet, but it's very likely because you see here, whenever this PR2 reaches, right? PR2 reaches, you have to wait for another cycle to latch it.
Gotcha.
So that's probably why it's adding 1 more cycle to it. It's adding 1 more cycle to the period, not to this guy. This guy's not changing. Why? Because that 1 more cycle, it will be added to here. So it's extending that time by 1 more cycle, by 1/4 of microseconds. And then after this is latched, it'll start counting, it'll clear the timer and start counting for this time. That's something else. We don't have to worry about that. That answers your question, okay? Why? I don't know. It's probably just need 1 more cycle to keep it secure. So it's not being interfered by other flip-flops. That's less important though, okay?
So the high is just there. So basically, turns on, turns off, and then
It's
as
being
soon as
latched.
the timer resets, it'll hold it in the high.
Yeah, and compare with the timer
Got it.
for the duty value.
Okay.
But we don't have to worry about that. It's some internal structure in the circuit. Well, we just it's duplicated, so it's not changing the number. Duplicate it.
And we're thinking that's probably because if you have like a changing pulse length every time.
Yeah.
Yeah. Okay, that makes sense.
Mhm. Okay. Remember 25? Okay. I'm gonna give you more numbers to let you calculate it, and you let me know. Okay. I'll let you verify it for me. All right. Let's try to show you here. That's all right. So it's a 1-to-1 prescaler. Okay? It's a 1-to-1 prescaler for timer 2. How long it takes?
For 25 counts?
For 25 counts. Calculate it and let me know. Why do I know timer 2 is 1-to-1 timer prescaler? Since I said it. Oh, it's 1-to-4? Oh, sorry, 1-to-4. 1-to-4, sorry, 1-to-4. 1-to-4 prescaler for timer 2, 25 for the duty counts.
Can't remember if you said this already. Is prescaler always going to be given in the problem?
Yes.
Okay. So we're not going to have to know.
No.
That's yeah.
Is this a multiple choice test or is it like
Calculations.
so you get partial credit if you get like
Yeah. So we have tomorrow, Thursday. I will be in the first section. If you have questions, you can come and ask questions. And for the TAs, most of the TAs will be, unless they announced it otherwise, they will be in the sections. You can ask questions as well during the lab sections. What's that?
For the answers, it's just 0.39 meters, or 0.39
No.
seconds.
So it's 1-to-4 prescaler.
Oh, sorry.
So how do do that? 1-to-4 prescaler. I'm sorry. So 25, do what? 25 is the counts, right? Given the counts, calculate the time. You just need to know the frequency. Its frequency here is 64. With the 1-to-4 prescaler, it's gonna be 16. Okay? 16 megahertz for that 25 counts. You can calculate the time. How long?
1.5625.
Okay, 1.56. Okay? Let me show you. I verified it for you. What is the delta X?
That's pretty close. Yeah.
What's the period? 26 microseconds. It's not within our calculation. However, it was set as 26 microseconds because the PWM period is 30 kHz. So that's why it has to be 26 microseconds. Is this 10%? I'm sorry, wait a second. Is this 10%? 1.5 microseconds and 26 microseconds. Is this 10% duty cycle? No. If you see 10% on the in-lab or the lab, it's wrong. It's not 10%. Don't get confused. This is correct. Why? We verified. I probed it. Has to be right. What's that?
On the test earlier, you were mentioning something about like adding 1 to PR2 to get how long the duty cycle really is.
Yeah. Not the period, not duty cycle.
Period.
Yeah.
Will that be something you need to worry about on the test, or is that?
It's gonna be on the test. I told you, right? I talked about this for a long time. Let's see. PR2, do the calculation, find out the period. This number, you have to know the frequency, given the count, find out the time for the duty value, for the duty cycle. It's just one page. Study it. Have questions, visit office hours. I will be there for the whole afternoon. Tomorrow, Thursday, first section, 3 hours. I'll be there. For the rest of the day, TAs will be there. We'll see how that works. Worst of cases, we'll delay it to Monday. Probably it's too hard because people already schedule the test for the testing center. It's hard. So I don't know.
You said
What's that?
testing center? I thought it was in class.
Oh, I mean for people who are taking that in the testing
Where
center.
in there is the calculation for the period? I'm
Here.
okay.
Period. Yeah. You'll give us a number of counts to determine period, right?
Yes.
Yeah.
Yeah, with the counts.
Counts plus 1 over FOSC divided by prescale.
No. FOSC divided by 4 divided by prescale. Because of this.
Because that's for like timers. That's not for timers.
Hard.
We need to get the IR to like turn shit on.
We got
That'd be
it.
so
We got it.
So when we pull up the VW, right? With our laptops out, pull it out, plug in the pig board, right? Pull up, get the serial port connected, and then we hit a button, and then it